Hello. Oh, so in this lecture, I'm going to discuss about the synchronous counter. Okay, how a synchronous counter is designed, that I'll discuss in this lecture. So, I think all of you know what is the meaning of synchronous counter. Synchronous counter means in this counter, whatever the flip-flops will be used, clocks will be applied to all the flip-flops at the same time. Means synchronously clock will be applied. Okay. Now, first of all, what is the meaning of counter? Counter is nothing but the combination of some flip-flop. Counter is nothing but the combination of some flip-flops that will do some count operation. Okay. This is the meaning of counter. Now, what is the meaning of synchronous? Means the number of flip-flops are used to make this counter in all the flip-flops, the external clock will be applied simultaneously. So clock will be applied simultaneously in each of the flip-flop. Okay, this is the meaning of synchronous. Okay. So in this lecture, I'll show what are the steps you need to follow to design a synchronous counter. So for example, we can take this particular problem. Suppose the question is given, design a synchronous 3-bit up counter using JK flip-flop. This question is suppose given to you. Now how to find the solution? So you need to follow some step in order to get the solution. Okay, in order to design this synchronous 3-bit up counter, you need to follow some steps. Okay, so what is the first step? Step number 1, you need to determine how many flip-flops you need to use. So the number of flip-flops will be equal to the number of bits. So as it is given 3-bit, so how many flip-flops you need to use? 3 flip-flops you need to use. Now, why I am saying number of flip-flop will be equal to the number of bits? So I think all of you know each flip-flop can store 1 bit. Each flip-flop can store 1 bit. So as you have 3-bit up counter, so in order to store 3 bits, you have to use 3 flip-flops. Okay, so that's why the number of flip-flops should be 3 to design the counter. So that is the first thing you need to determine. Then the next thing is you need to make the truth table for the counter. So step number 2 is you need to make the truth table for the counter. So how to make the truth table? And from the truth table, not only you need to make the truth table, from the truth table, you need to find out the value of the different flip-flop inputs. Means for this problem, as the question is given, means you have to use JK flip-flop to implement this counter. So you need to determine the value of J and K. Okay, for all the flip-flops. How many number of flip-flops you are using for each of the flip-flop, you need to determine the value of J and K. Okay, now how to make the truth table? That is very important to understand. Okay, so in the truth table, you need to write few things. Present state, you need to write next state, and you need to using these three things, you need to find out the value of the different inputs. So I'm considering first flip-flop is flip-flop number A, flip-flop A. You have flip-flop B, you have flip-flop C. So I'll start from flip-flop C. So present state, next state, and the different combinations. So suppose present state, you have QC for flip-flop number C, you have QB for flip-flop number B, and you have QA for flip-flop number A. And the next state is denoted by QC plus 1 for flip-flop number C, QB plus 1 for flip-flop number B, and QA plus 1 for flip-flop number A. Now, using these things, we need to determine the value of JC, KC, means the input value of flip-flop number C. Then the input value of flip-flop number B means JB, KB, and the input values of flip-flop number A, that is JA, KA. So these three things, this 2 means six things you need to determine. Okay, from the truth table. Okay, so how to do that? Okay, so how to do that? So we can write here it's JC, KC, JB, KB, and JA, KB. Now how to do that? So as it is a up counter, 3-bit up counter, so let me write down 3-bit. So if your present state is 0, 0, 0, and as it is a up counter, so what will be the next value? The next value is 0, 0, 1. Okay, how I am doing? So as it is a 3-bit up counter, actually you need to understand what are the values it will count. It will start from 0, the next count will be 1, then the next count will be 2, then the next count will be 3, then it will be 4, then it will be 5, then 6, then 7, then 0. Then again come back to 0. So how many counts it is doing? Total 8 counts. Okay. 3-bit up counter means how many counts it will do? Total 8 counts starting from 0 up to 7. 0 to 7 means total up count. And as you are using 3-bit, why you are using 3-bit? Because as you have 8 different states, so in order to represent 8 different states, you need to have at least 3-bit. That is well known to everyone. Okay, so let me write down those things also here. As you have 8 different states, okay, each of the state has to be represented by 3-bit. That is well known to everyone because you know the formula 2 to the power n equal to the number of states. So in this problem, the number of state is 8 and you need to determine the value of n, that is nothing but 3. And this is deciding the number of bits you need to use to represent each of the state. That n is nothing but number of bits required to represent each of the state. That you need to understand. Okay. So it means how many bit you need to use? 3-bit you need to use. So 0 has to be represented by 3-bit. Then 1 also has to be represented by 3-bit, that is 0, 0, 1. Then 2 also has to be represented by 3-bit, 0, 1, 0. Then 3 also you need to represent by 3-bit, that is 0, 1, 1. Then you have 4, you know very well, 1, 0, 0. Then you have 5, 1, 0, 1. Then you have 6, 1, 1, 0. Then you have 7, 1, 1, 1. And then you need to come back to 0. Okay. So these are the counts it has to do. So if you start from 0, 0, 0, what will be the next value? Definitely 0, 0. So try to understand. So as your present state is 0, 0, 0, what will be next state? 0, 0, 1. Now if you consider the present state is 0, 0, 1, what will be the next state? 0, 1, 0. If your present state is 0, 0, 1, if your present state is 0, 0, 1, what will be the next state? 0, 1, 0, that is nothing but 2. So you write 0, 0, 1, 0. Now, similarly, if your present state is 0, 1, 0, the next state will be 0, 1. Okay. So what I am trying to say, if your present state is 0, 1, 0, then the next state will be 0, 1. And follow the same procedure for each of the state. So if your present state is 0, 1, 1, next state will be 1, 0, 0. And if your present state is 1, 0, 0, next state will be 1, 0, 1. If your present state is 1, 0, 1, next state will be 1, 1, 0. If your present state is 1, 1, 0, next state will be 1, 1, 1. If your present state is 1, 1, 1, then you have to start from the beginning. Then the next state will be 0, 0, 0. Okay. So it means if your present state is 0, next state is, so 0, 0, 1 means this is nothing but 1. So if your present state is 1, next state is 2. If your present state is 2, next state is 3. If your present state is 3, next state is 4. Like that only. If you come to present state of 1, 1, 1 means 7, the next value will be definitely 0, 0, 0. That is 1. That is 0. Okay, that we have observed here. If your present value is 1, 1, 1, if your present state value is 1, 1, the next value will be 0, 0, 0. Then this is the thing we have shown. And after that, no need to see the next because you have to do the same operation again and again. So you need to stop here. No need to do any further means process. You no need to apply again 0, 0, 0, then 0, 0, 1 because you have already done here. Okay, you need to stop. Now, using these things, you need to determine the value of JC, KC, JB, KB, and JAK. Now, how to do that? So, in order to do that, you need to know the excitation table of JK flip-flop. So, you first write down the excitation table of JK flip-flop. So, what is excitation table? If you know the value of Qn and Qn plus 1, means if you have the present state value and next state value, from there you need to determine the value of input J and input K. Okay. So, this is known as excitation table. So you need to know the excitation table of JK flip-flop, then only you can design this thing. So okay, how to do that? To make as you have this Qn plus 1 value available to you. So you write down these values. If you have two variables, how many combinations are possible? 4 combinations: 0, 0, 0, 1, 1, 0, 1. And using that, you need to find out the value of J and K. So the excitation table of J and K is nothing but for 0, 0, it is 0x. For 0, 1, it is 1x. And for 1, 0, it is x1. And for 1, 1, it is x0. How this excitation table we got? To understand that, you can check my JK flip-flop excitation table and truth table video lecture. Okay. So these values you need to put in the in this truth table in order to find out the value of this JCKC, JBKB, and JAK. Okay. So we'll start from this one. So compare the QC and QC plus 1 value. What are the values? 0, 0. So you see the excitation table. If it is 0, 0, what should be the value of J and K? That is 0x. So you write down 0x here. Why I am writing down here only? Because I am considering QC and QC plus 1. It means that I am talking about the flip-flop number C. So you need to put the value in flip-flop number C only. That is JCKC. Okay. Now check the next combination. This 0, 0 again. This 0x. Then 0, 0, 0x. Then 0, 1. So if you have 0, 1. Then what you need to put in J and K, that is 1x. If you have 0, so you put in here 1x, then 1, 1. According to excitation table, if it is 1, 1, it has to be x0. So put x0 here. So if it is 1, 1, again x0, 1, 1, x0, 1, 0, that is x1. 1, 0, you check. 1, 0 is nothing but x1. Okay. Now follow the same procedure for all the flip-flops. Now do the same thing for the second one. Now compare QB and QB plus 1. You have 0, 0. 0, 0 means 0x. Then 0, 1. 1x. 1, 1. That is x0. 1, 0. x1. 0, 0. 0x, 0, 1, 1x, 1, 1, x 0, 1, 0, x 1, 0, x 1. I did not write this value, that is 1, 0, that should be 1. Okay. Now do the similar procedure for the third flip-flop also. So follow the same procedure, that compare this q and qa plus 1. This 0, 1, 0, 1 means 1x, 1, 0 means x1, 0, 1 means 1x, 1, 0 means x1, 0, 1 means 1x, 1, 0 means x1, 0, 1 means 1x, 1, 0 means x1. Okay. Now go to step number 3. What you need to do? You have to find out the values of JCKC, JBKB, JAKA. So all these 6 variable values you need to find out. How to do that? Using KML. So in the KML, what should be your input variable? These are the things should be your input variable. What are the things? QC, QB, and QA should be your input variable. And using these things, you need to find out JC, KC, JB, KB, JA, KA. So do that. So you'll go to step number 3. So find out for first one, that is JC. So 1, 0, 0, 0, 1, 1, 1, 1, 0. And the variables are QC, QB, and QA. These are the 3 variables: QC, QB, QC, QB, and QA. Okay. So see the values. What are the values? Are there? 0, 0, 0, 1. So put these values in the KMF. 0, 0, 0, 1. According to the position you need to put. Then X, 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 X. Don't care, don't care, don't care. Okay. So from this, if we make this pair, what will be the expression? That is nothing but QB, QA. Okay. Now follow the same procedure for the next variable, that is KB. Next one is KB. You have QC, QB, and QA. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now see the KV values. Sorry, KC values. You see, it should be KC now, because I am first finding out the values for C flip-flop. So JC I already found out. Now I need to find out for KC. So you see the KC values. Don't care, don't care, don't care, don't care. Put it, don't care, don't care. Then you have 0, 0, 0, 0, 0, 0, 0, 1. This procedure we need to follow according to KMM. If you command this one, what we are getting? QB, QA. Okay. Now do the same procedure for the second flip-flop inputs. So for the second one, again, your variable QC, QB, QA. Now you need to find out JB, as well as you need to find out KB also. Okay. First find out JB. 0, 0, 0, 1, 1, 1, 1, 0. So see the JB values. JB value 0, 1, X, X. Sorry, no, 0, 1, X, X. 0, 1, don't care, don't care. Then you have 0, 1, don't care, don't care. 0, 1, don't care. 0, 1, don't care, don't care. Now, if we make a quad using this 4, then what we'll get? We'll get Q, A. Okay, according to Ken. Now do the same thing for KB, QC, QB, QA. These are the input variables 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now check the KB values. X 0, 1, X 0, 1, then X 0, 1, X 0, 1. So we can make a word using this 4. So its value is nothing but here also it is QA. Okay, now follow the same procedure for flip-flop number A. In this case also we need to find out JA. We need to find out A. Variable QC, QB, QA. I can use different variables. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0. Input is QC, QB, QA, 0, 1. Now check what the values are there for JB. 1 don't care, 1 don't care, 1 don't care, 1 don't care. So these are 1 and don't care alternatively. So right. 1 don't care, 1 don't care, 1 don't care, 1 don't care. So all the positions of the KMF are occupied. So it means it's nothing but 1. So similarly here also don't care, 1 don't care, 1 don't care, 1 don't care, 1. It means all the positions will don't care, 1 don't care, 1 don't care, 1 don't care, 1. So it means all the positions are occupied by either 1 or don't care. It means here also the result is 1. Now our job is almost done. We need to do the last step. Step number 4. What do we need to do? We need to make the circuit. Step. We need to make the proper combination of the flip-flop to make the counter. Okay. So what are the flip-flops are there? 3 flip-flops are there. That is flip-flop number A, then flip-flop number B, then you have flip-flop number C. And each of the flip-flop having 2 inputs, JA, KA, and 2 outputs. That is, we can write QA bar. Then for B also 2 inputs, JB, KB, and 2 outputs, QB bar. And for C also 2 inputs, JC, KC, and 2 outputs, QC and QC bar. Okay. Now we'll check what expression we got for each of the case. JC we got QB and QA. So JC we got QB and QA. Now check where is QB. This is QB and this one is QA. What value of this thing we got? We got JC equal to QB and QA. It means that it is having some AND relation. Oh, why have written that? It's having some AND relation. Check the expression. That is AND relation between QA and QB, and that is giving the value of JC. So QA and QB and gateway views that you need to give in JC. Okay, you need to connect it to the input terminal of JC. Now, for KC also what you got? You got QB QA. Okay, so QB QA result we are already having here. So you can make it short. So it means that KC is also having this input of QB and QA. Okay. Now check the next one. The JB is QA, KB is also QA. Where is JB? JB is nothing but QA and KB is also QA. So what you can do, you can make these 2 things short and you can connect it. Because JB, KB both are QA only. Okay. Then see the last one, J and K. What about J and K? J equal to 1, K is also 1. So make J and K short and give the value of logic 1 here. Okay, so this is the implementation of the up counter using JK flip-flop. Now still one more thing we need to give in the circuit that is so much important. That is the clock. We need to give the clock. And you need to apply the clock to each of the flip-flop. Because it's a synchronous counter. So your external clock has to be given to each of the flip-flop simultaneously. Okay, so this is the design of a up counter, 3-bit up counter using JK flip-flop. Thank you.